All right, hello everyone. So today we're working on an improper integral. Does the integral that goes from 1 to infinity of quantity cosine of x plus 2 divided by quantity x to the 1/3 plus e to the x dx converge or diverge? Okay, so we could try to integrate that directly here, but that's really difficult to do. What I mean by directly is by using some kind of integration technique. But that's not going to work out really here. So you want to use an alternative here, which is the comparison test that we have for improper integrals. There's another comparison test for series, that's something else. But actually they're very similar results. But anyways, we have the following. First of all, if you have a function, two functions, f and g, they're both positive, and f is less than or equal to g, then we have the following results. If the integral from a to infinity g of x dx converges, then the integral of a to infinity f of x dx converges. So in other words, if the integral of the bigger one converges, then the integral of the smaller one is going to converge as well. And part B says if the integral of the smaller one, so if the integral of a to infinity f of x dx diverges, then the integral from a to infinity of g of x dx diverges. So if the smaller one diverges, so does the bigger one here. All right, so we're going to use this theorem to solve this problem. And the way this theorem works is that you have to come up with a function to compare your integrand to. So our integrand was cosine of x plus 2 over x to the 1/3 plus e to the x. So I'm trying to look for a function that's either smaller than this or bigger than this. Now, is it often the case that it's easier to make, especially when you have a plus on the denominator, to make a less than, go this way? And yeah, so that's what I'm going to begin with. I'm going to make a bigger fraction by, first of all, I'm going to keep the same denominator, so cosine of x plus 2, but I'm going to do this. I'm going to just have e to the x here, and that is a legit move. If you have two fractions and one of them, the fractions are positive, then if you basically have a fraction with a smaller denominator, that fraction with the same numerator, that fraction will be bigger. So just think for a second about 1/5 and 1/4. 1/5 is less than 1/4, is what I'm trying to get at. They have the same numerator, but the denominator of 4 is smaller than 5, so overall that fraction 1/4 is bigger than 1/5. The same thing here is what we're getting at. All right. So the next thing I'm going to do is as follows. I'm going to make this function a little simpler, and I'm going to work with another inequality. We know cosine is between -1 and 1. So the largest cosine could ever get is 1. So this expression on the numerator, the biggest it could ever get would be 1 plus 2, 3 over e to the x. So I want to work with this right here, and I'm going to make that my function. That's like your g of x, okay? So again, you make an inequality in any which way possible. And there are several ways of doing that as well, by the way. And then at the end, what you want to do is you want to take your integral. So I'm going to take the integral that goes from 1 to infinity of 3 over e to the x. So you want to try to simplify this as much as possible. And this would go from 1 to infinity 3 e to the minus x dx. And if you rewrite this in terms of the notation for an improper integral, it looks something like this. And I'm not going to go through all the steps here in terms of the integral, but it would look something like that. And if you plug in b and you plug 1 in, you get this right here. And what's going to happen is, since this limit, this right here, e to the minus b, I'm sorry, that was not a good minus b there. This is going to go to 0, and this is just going to, so it's going to be 0 plus 3 e to the minus 1, and therefore that integral converges. And since the integral 1 to infinity of 3 over e to the x dx converge by the comparison test, so does the integral that goes from 1 to infinity cosine of x plus 2 all over x to the 1/3 plus e to the x dx. That's what that theorem says, okay? So I don't need to integrate this directly, just because a larger function converges, so does this one. Now, one thing I wanted to mention here is with the inequality, that's not always easiest thing to do for a lot of people, because many of you probably don't have a lot of experience with inequalities. Certainly, you see inequalities once or twice in a calculus class, mainly in calculus 1. So a lot of people ask me, well, if you take that same expression, couldn't you have done something, for example, like this? Instead of putting the e to the x, putting the x to the 1/3. Yes, this, for example, would work out, and this would have worked out to be 3x to the 1/3. So it is certainly the case that this is less than that. The issue, though, would have been this. When you integrate 3 over x to the 1/3 dx from 1 to infinity, that's going to diverge. And if the bigger one diverges, that doesn't say anything about the smaller one. Let me go back to the theorem. Yeah, the theorem only says if the bigger one converges, then the smaller one does, and if the smaller one diverges, then the bigger one will do the same. It doesn't say anything, if the bigger one diverges, something about the smaller one here. Yeah, nothing like that. So you have to be careful when you're picking your inequality. Now, after some practice, you tend to get good at knowing like what's gonna converge or diverge. So anything with x to the 1 over something is usually going from 1 to infinity, let's say, is or a number to infinity, that's usually gonna diverge. So you would be careful making your inequality. Now, I will make another video where I speak about using the comparison test to show something actually diverges here. But just wanted to introduce this topic here. And again, you basically try to make an inequality. You want to keep it, your function, as simple as possible, the one you're going to integrate. So we did here with 3 over e to the x. And then from there, you establish that result. Okay? All right. Well, thank you so much for your time. Hope this helps.